Let's see. So the topic of today's webinar is Hazelcast HD memory. We're going to look at the world of big data and low latencies. Our presenter for the day today is Jaromir Hamala. He's a engineer here at Hazelcast, and I'm going to go ahead and turn the webinar right over to Jaromir now.
So, ladies and gentlemen, hello again. So, as Ben said, my name is Jaromir Hamala, and I work as a core team lead at Hazelcast. And today we were talking about the HD memory. A few words about myself. Well, I like to brag that I wrote my first line of code when I was 6 years old. So I learned to write basically in order to code. And yeah, I'm a big open source fan, and actually I joined Hazelcast after a few months of contributing. I like to tell a story that I was a consultant by day and the Hazelcast hacker by night, and this was going on like this for a few months, maybe half a year, and I was quite happy, but people around me, especially my girlfriend, was less happy. So after about 6 months of contributing, I was like, guys, maybe you could pay me for coding Hazelcast, and they were like, yeah, okay, why not? So that's how I joined Hazelcast more than 2 years ago, and I've been very happy since then. So what is on today's agenda? So we will do some very brief overview of garbage collectors in the HotSpot JVMs. Then we'll look at what the hell is the HD memory. We'll see some short demo. We will briefly discuss use cases at the end of the presentation. There will be a room for your questions. So what's the problem? So RAM is the new disk, as Jim Gray famously said, and of course RAM is cheap, it's everywhere, and we want to use it. As a Java developer, we want to use all that RAM which is cheaply available. There's one little problem, and the problem is called garbage collector, or I wouldn't dare to call it a problem really, but yeah. So if you are a Java developer and you started to code more than a few months ago, you are probably aware of this little issue when you want to use massive amounts of RAM from Java, and you want to keep predictable latencies. The word predictable, this will be one of the words I will keep repeating over again during this presentation, because predictability is what matters, and predictability is the main reason why we have the HD memory, as we will see during this presentation. Just a small clarification, this problem with massive amounts of memory is of course not specific to Java, but yeah, it's quite visible there. So what is the problem with massive memory and a garbage collector? So with a little bit of oversimplification, almost all garbage collector algorithms, certainly the one which are in the hotspot and in the JVMs derived from the hotspot, they work quite similarly. Somehow they mark all live objects, and then they will just reclaim the objects which are not marked. And there are some variations. They attempt, some algorithms might attempt to do some parts of the work concurrently while your application is running, but still this is pretty much the idea. And depending on many factors, mostly on your SLA, it's quite often impractical for bigger heaps. The exact borderline really depends on your SLA, on your requirements, but typically it's about 10 gigabytes, where in the normal application it's starting to be visible. It's starting to be a pain. Of course, if you are in a domain of high frequency trading, you have totally different requirements. But this is something very typical. We rarely see JVMs with tens of gigabytes of heap. And yeah, in the agenda, I didn't mention the NAP, but there was a picture. So if you happen to know the book on this slide, then you can really take a nap for a few minutes, because yeah, I will briefly discuss what we have in the hotspot. So we have three main garbage collector algorithms. The first one is the parallel alt garbage collector, which is non-concurrent by design. It means it's designed to stop your application while it's doing its job. So that kind of gives away that it's not a good choice when you want to have real time or close to real time or soft real time behavior, because when the parallel old garbage collector is running, your application is not that simple as that. Then we have the concurrent mark and sweep, which is mostly concurrent. It means that mostly your application can run while the CMS is doing its job, but it's mostly. So there are phases which are not concurrent, and while these phases are in progress, your application is again stopped. And also it suffers from fragmentation. It means it's not a copying garbage collector, so eventually your heap may become fragmented, and then you may have concurrent mode failures, and then there will be a fallback to the plain old non-concurrent garbage collector. It means again your application will be stopped. And beside that, there are some concurrent failure modes. The simplest one is that when you have a high mutation rate of your objects and the CMS is not keeping up, then again it will fall back to the plain old non-concurrent GC and your application will be stopped. Then we have this famous garbage first G1 collector, which is again mostly concurrent, but again there are some failure modes when it's not keeping up. Also the G1 garbage collector is trying to be clever, so it will split your heap and then into the regions, and then it will try to garbage collect each region separately or not in one go, in order to make the poses bearable. This is great idea, but then it means that it needs to maintain references from one region to the other, and the bigger heap you have, the more regions you have, and therefore more dependencies or inter-region dependencies you will have. And again, the pauses will grow with your heap. So yeah, not a really great. We do not have a single low pause or pauseless. We do not have a pauseless garbage collector in the hotspot. And why it matters? So I mentioned that the predictability will be the word which I will keep repeating over and over again. And the second word, which or an acronym, I will keep repeating, is the SLA. So our agreement, service level agreement, what we have to deliver in order to satisfy the business. So what is our, let's say, the worst case latency or worst case pause we can tolerate and still do not breach our SLA. So that's typically the most important reason, of course. And then it can be something as simple as that waiting is annoying. So Amazon published a study which was quite interesting. It revealed that that the longer the page takes to load, the higher chance that the customer will just close it, because people do not like waiting. So it can cost real money. If you are in the domain of electronic or high frequency trading, then it will cost you real money, and that's obvious. So it matters. What we can do about it? So the usual design or the advice is, okay, so you can't scale up. You can't just keep adding RAM because, JVM doesn't like that. Then, maybe you can start multiple JVMs on the same box, and that's usually works pretty well. So if you have a big box with 700 gigabytes of RAM, then maybe instead of trying to run a single JVM with all this RAM as a single heap, you could start 100 smaller JVMs, and each with about 765 gigabytes of heap. And then you can hope that a single request will never ever hit all all the JVMs at the wrong time. So that usually works, and you can't. So what's the problem with this? One issue is that it's pain to maintain. So now instead of maintaining one JVM, you have to maintain 100 JVM. That's one problem. That's obvious. This is partially solvable with modern DevOps tools. So you can use automation and whatnot, but still, single JVM is a single JVM. The other possible issue is that your data locality may suffer. So just an example, if you have 10 JVMs, then there is a chance that, well, every 10 item will be stored locally inside your local JVM. Hence, when you want to access it, you do not need to go over the network, which is usually pretty expensive when compared with some local algorithm execution. So that's 1/10 of your data are local. But when you are running 1,000 JVMs, that just 0.1% of your data set is local to your JVM, and for 99.9% of your data, you have to go over the network. So you can imagine that's not always great. If normal network typically have the round trip latency about 100 microseconds, quite often more. So yeah, the 100 microseconds is a lot of time. So yeah, scaling out is not always a viable option. So what else you can do? Maybe you could use a different JVM which has a pause-less or extremely low pause garbage collector. That sounds good. The little problem is that there is just one JVM on the market which really has a low pause algorithm, which is Zing JVM. It's not really mainstream. Of course, it's not open source. Developers are not typically familiar with Zing JVM, and yeah, it's something. It's not something you will commonly find in the normal stack. The other problem with all these garbage collector algorithms I was talking about is that both CMS and G1 they work on the old generation of your heap only. It means that the young generation is always garbage collected as a stop the word. It's a stop the word event. Typically, it's not a problem, but when we are talking about massive heaps of hundreds of gigabytes, then even the young generation space will be quite big, and that can result in a rather big or long GC pauses, and there is not too much you can do about it except for some tuning. And yeah, and it's a pain, as I already mentioned, it's pain to maintain thousands of JVMs and pay support for them if you need to have a support. So before we start talking about the actual HD memory, one clarification: do not get me wrong. So it may seem that I was almost trash talking garbage collectors. That would be an utter misunderstanding. I love garbage collectors. They are great. And if I'm writing a business code or almost every code except some system programming and a middleware, then I definitely want to use it. I do not want to deal with dangling pointers and segfaults and low-level stuff like this while I'm working some business code. That I do not want to do that. So the price is typically very low. Well, maybe except when you have massive amounts of live objects in memory, such as in the case of in-memory data grid. Yeah, so do not get me wrong, I love garbage collectors. So that's just a small clarification. Really, what they give you, this garbage collector, is really this great illusion that you have unbound memory, that your memory is endless and you don't need to care about freeing up your memory, and this is just great for programming. So what we can do better, what I can do in order to have a freedom to choose whether I want to scale horizontally, whether I want to scale out by having multiple machines, or whether I want to scale vertically in order to just have small amount of machines and just load them with RAM and CPUs. And I want to have a freedom. I do not want to be constrained by some technical limitations of my JVMs. I want to be able to have tens and hundreds of gigabytes of RAM per JVM, because that's not that uncommon in the servers. In our lab, we have machines with, I believe, 768 gigabytes of RAM, and I believe it's not really that uncommon. So I want to use it. So how I can use it? Well, that's what this webinar is about. So HD memory, one clarification: it does not stand. The HD does not stand for high definition. People sometimes ask. It stands for high density, because that's what it is. You can really pack your server and densely. You can have small amount of JVMs really and use all the memory available, while keeping, that's the important bit, keeping your latencies down, and most importantly, predictable. So your latencies will not grow with your data set. That's really the most important message. The advantage is obvious. So the system consolidation, that's the first one. So instead of maintaining hundreds and thousands of smaller boxes or smaller JVMs, I can have just a few of them and a large one. It means that I have less moving parts. It's easy to maintain. It's easy to design for this, and you have this much improved data locality. And at the same time, you can have a predictable latencies. It will be deterministic. So how it works? It's no magic, really. It's if you are just a somewhat experienced developer, you can probably imagine how it works. So technically, on the technical level, the current implementation, it uses native, aka off-heap memory. And then we have another implementation which does not use off-heap of Java heap memory. It uses on-heap, but it maintains the memory on its own. So instead of having a Java object per each item stored in the map, we will just ask JVM to give us some large continuous block of memory from heap, and we will maintain it ourselves. I think we'll go into the greater details later. So the default implementation, or the current production implementation, is based on off-heap memory. So we'll just ask operating system, okay, give me a block of memory. And from now on, we will just maintain it ourselves as they are requests. We have our own memory manager implementation to do pooling and things like this. What's important, and perhaps not unique, but not too common, at least not when it comes to the off-heap and Java world, is that a memory allocator is memory alignment aware. It means it will work even in architectures like Solaris on Spark, which have requirements to have aligned memory. It means that I can't just use some random or address willy-nilly. I need to use aligned memory addresses, and the HD memory is aware of this. It means it works even on a Solaris Spark at the latest version. So that's the default implementation. And the other one is what I have mentioned. So in the case where the off-heap memory is not available for some reason, we have a design and prototype ready where we can use this on-heap memory, but from the JVM perspective, instead of having millions of small objects which are costly to track for this garbage collecting and for this marking phase and things like this, it will appear as it was just a single or just few of massive objects, and it means it will be pretty easy for JVM to track these objects. So it means that even when the actual heap will be large, because now all the data will be stored on heap. It will be still relatively cheap for JVM to run the garbage collector. So again, the post time will not grow with our data set. So what the things I have discussed so far, they are at a low level, and of course, as Hazelcast users, you are used to simple and nice to use API. At least that's what I like to think. So all this is exposed to you as a configuration option for some Hazelcast data structures. So not for all of them, but for the two most popular. So the absolutely most popular Hazelcast data structure is IMAP, is our bread and butter really, and that. If you are not familiar with IMAP, it basically is a distributed implementation of the concurrent map from the Java concurrency package. It literally implements the interface. And if you are using the regular concurrent map, then you can switch to a distributed implementation and still keep the same API. And once you have Hazelcast, then you can switch again to the implementation backed by the HD storage just by a configuration, just by configuration change. What's important here, or very important, I believe, is that if you are using the HD IMAP, then both keys and values are kept in the HD memory because some other projects and product they keep just the values in memory, so we keep both keys and values in the HD memory. So there are so again your heap can be tiny really, and also the metadata. So metadata, you can imagine you have an IMAP and the IMAP has some sort of statistics. So you have a TTL and you have the last access time and the last mutation time. So all this metadata are also stored in the HD memory. So your actual heap can be really tiny, which is great. That's what you want. So I promised you some demo, and I also promised that the configuration is pretty simple, or switching from the regular IMAP to the HD IMAP is simple. So this is an example of the declarative configuration. So what I have to do is, instead of using the default data in memory format, I will use native, which stands for the HD memory. For historical reason, it's called native. And then I need to configure my native memory area. So that's the second part here. You can imagine this to be similar to the XMS flag. When you are starting JVM, you need to specify, okay, I want to use at most this much of memory for my JVM heap. So this is something kind of similar. So you can specify, okay, so I want to use at most 100 gigabytes as my HD memory. And I want, you do not need to specify the other attributes. We will use a reasonable default. So just for your info, this pool means that we will allocate, or we will ask the operating system for the memory just once, and then we will maintain it ourselves inside our internal memory manager implementation. And the 15% of this memory space will be used for some internal metadata of the HD data structures. And I believe now it's after 20 minutes of talking, it's time for some short demo. So what I have here prepared is some very basic benchmark. It's doing just get and put into the IMAP, which is running on 9 members in our lab. And the actual configuration is not really important. It's fairly basic test. It's using a rather small amount of data because I do not want to wait 15 minutes to have some initial data load during this webinar. So the test will start 9 Hazelcast members. and then it will load some initial data, and then it will do put and get, and we'll see some basic, very basic performance data. So I can see that it's really string test, and I'm using just 500,000 keys. So this is, and each has about 10 kilobytes, the value length. So this is fairly basic test, but what will be important here is the maximum pause time. So I haven't specified any warm-up time, so the first line is not really that relevant. But the second time should be, yeah. So I can see that my throughput is about 130,000 operations per second. That's okay. Average latency, which is not relevant at all in this case. What is important, there are two things which are important. First is 2016, and yet I can't see the micro symbol from the Unicode here. And the more important here is the maximum latency, which is about 300,000 microseconds, so 300 milliseconds. Almost half a second. So now it goes down because I believe there was no full GC at all, because I have a small data set and rather large heap. But you can see it's quite on a high side, and it's not predictable. That's the important bit. I could apply some tuning, but still the idea stands that the longer the heap is, the larger the heap is, the longer the pause will be. And I do not want that. I want to have a predictable latencies, predictable pauses, which will not grow with my data set. What I can do is, well, use the HDI map. So I need to do some configuration changes. So the first change here is, well, I will enable the configuration. So I have this native memory space at most 500 gigabytes, and for all maps, all IMAP starting with the name string with this prefix, I want to use the native in-memory format. So that's the first change. And the second change is that I will just change the heap size. So I will not use the 100 gigabytes heap, I will use just 3. I believe I could use very smaller heap. Okay, let's try it now. So now I'm starting the version with the HD memory. So it's the very same test. Everything is on default, including the garbage collector, and all this native memory options are on default. And what we should see is roughly the same throughput. That's important bit. Sometimes people ask me, okay, is HD memory much faster than the non-HD or non-HD IMAP? The answer is, when it comes to the rough throughput, it's roughly the same, because the throughput is dominated by the network latencies, and there's not much you can do about it. But where the difference is really the maximum, the worst case latency. So in the case of the IMAP, we could see that here we had latencies for about 300 milliseconds, and that's really with a rather tiny data set. But to be fair, with default garbage collectors. And here you could see that the maximum latency is about 10 milliseconds, and it should stay like this. And what's important, if I had 100 times larger data set, then the pause time would be still the same. It would not grow with the data set, and it would be still nice and predictable. Nice and predictable. That's the mantra here, really. So that was the very basic demo, just to show you how simple it is to use. So no extensive configuration. You just switch the format, and you are done, and you can just decrease your heap size. The other data structure with the support for HD memory is JCache. So JCache is a specification or standard developed under the umbrella of JSR 107. There are other implementations, so Hazelcast just happens to be one of the implementers. You can see JCache as sort of JDBC for caching. So when you have a JDBC driver, then you can use the same API to access many different databases. So the JCache is something sort of similar. So you have one API and you can use it to access many different caching projects and products. The spec itself is really agnostic to the underlying data storage. So it does not care whether it is stored in memory or on heap, off heap, on disk. It doesn't deal with this concern at all because it's really just an API. And so our HD implementation, again, as it is the case with IMAP, so also with JCache, it stores everything, keys, values, and metadata in the HD memory, and the usage is really similar or almost the same as in IMAP. So you will just switch the configuration, okay? So for this cache or for caches matching this name, I want to use the HD memory, and you are done. Simple as that. So here is some, a chart from very similar, if not the same run as the demo I was showing to you. So the red line is the, the blue line is the latency with the default on-heap implementation of my storage. So that's the default case with Hazelcast. So you can see it's quite similar, HD, non-HD up to 99.99 percentile, and then suddenly the latency for the non-HD version just skyrockets. And I believe here at the y-axis is a mistake. The latency here is not this is not in milliseconds, this is in micros. So here the maximum latency for the non-HD was about half of a second, so not 500 seconds, half of the second. And the upper bound on the for the HD was still in small milliseconds, maybe 10 milliseconds is not really visible, but you can really see it's very low, especially when compared with the non-HD version. So what are the use cases for HD memory? I would say the use case is every time when you need predictability, every time when the non-deterministic behavior of the garbage collector implementations in HotSpot are just not suitable for them. Every time when you have SLA in the form, the maximum post time on 99.99 percentile cannot be worse than X. And if your X happens to be in the range of tens milliseconds and your data set is bigger than a few gigabytes, then you will have a hard time with the Java and heap. So that just frames the general use case. So every time when you want just to use massive amount of memory and have some predictability, have determinism, that's the use case. And yeah, so once you are using the HD IMAP or HD JCache, how we can monitor it? Because if we are using the regular Java heap, then we have a JMX, we have JConsole, and we have tons of product which can do the monitoring. So when you are in the HD memory, you can use the management center. So for monitoring Hazelcast, so you can see the utilization. Okay, so in this case, my maximum configured memory was 375 gigabytes. You can see that my machines are pretty much idle because I'm using just what 5% of my max memory. So okay, I have plenty of headroom. I could see that okay, there were two major GC events, but the overall post time was about 80 or less milliseconds. So that's pretty good. That's okay with my SLA. So that's one monitoring option. The second one is the Hazelcast diagnostic. So we can, in Hazelcast, you can enable diagnostic, and then we will print a bunch of diagnostic data into your file. Then you can scrape it, and you use whatever monitoring tool you fancy. And yeah, I mentioned at the beginning of this webinar that I'm from the development team. So I thought that I would share some implementation challenges with you. So every time in Java, when you go off heap, or in general, every time when you want to manage your memory yourself, then you will eventually face the issue with fragmentation. So in a nutshell, and again with a little bit of oversimplification, the memory fragmentation means, okay, so my overall utilization memory is not 100%, it's below, but I do not have large continuous block of memory anymore. And hence, if there is an allocation request for, a large block, then it may fail, despite that the overall utilization, is not on 100%. And in theory, there should be space, but there is not, because there is no large continuous block of memory. So in order to fight this, we are using the body allocation strategy for now, and seems to work pretty fine. The other challenge while implementing the off-heap or the HD memory is a concurrency control, because we no longer have the luxury of a garbage collector. So we need, normally we would need to take care, maybe do some reference counting to make sure, okay, now at this time there is nothing referencing these objects, therefore we can just reclaim the space. Fortunately, and this sounds like a nightmare to do from Java, really. Fortunately, the Hazelcast threading model helps us a lot in this case, because the Hazelcast threading model, basically we split all your data set into partitions, and then each partition is always accessed by a single thread and single thread only. And that's a great simplification, because we no longer need to deal with concurrency at all. And yeah, that helps a lot. And the third challenge was really this memory alignment. So when we were testing our HD implementation on a Solaris, we have realized, oh, okay, so we have to do a few changes here and there, because we can just use, can just access memory willy-nilly. There are some rules, and we need to account of these rules. So, for example, that we can access only memory which is aligned by 8 bytes, or rules like this. So these were these three, I would say, main implementation challenges. The great news is that you, as Hazelcast users, you do not need to deal with this at all. It's everything is being taken, is behind the scene, and we take care of this complications, let's say. So for you as ordinary users, you can just switch the flag, and voila, you are HD, and you don't need to care about any of these. So how you can use it? So the important bit here, it's a commercial feature. So this is not part of the Hazelcast open source offering under the Apache 2 license. This is a enterprise only feature. So if you want to try it, then you can go to this URL and download the trial version and really have a play. And please focus on the maximum or the worst case latency, the worst case post time, because it will not make your application magically 10 times faster, but it will make it predictable. That's the most important bit really here. And this is the end of the presentations I have prepared for you for today. So I believe now it's time to take some questions. So let me start the QA dialogue. So the first question is, with big on-heap memory, how do you deal with paging in and out? So we don't. We don't. It's simple as that. So when you, of course, when you want to use in-memory data grid, then you have to make sure that you have enough physical memory. If you are on Linux, then you can configure your swappiness. It's a ratio in between or an instruction for the operating system. Okay, how much am I allowed to swap? Would you prefer me to swap more in order to have bigger disk caches and buffers, or should I not try to swap as long as it is possible? Alternatively, you can always just disable your swap. That's not uncommon in a server environment, or when you are running in memory data grid, and that's the safest option. But of course, you need to have enough physical space. But I would say this goes without saying when you are about to run in memory data grid. So that was the first question. The second question is, can we cap the NIO usage? I believe it means if we can have a cap on the amount of memory or amount of native memory the Hazelcast HD will use. Yes, you can make a cap. So in your configuration, so it's exactly the same thing as with the regular on-heap memory. So you have this XMX flag to have a cap on your maximum heap size. With the HD memory, there is a Hazelcast specific option to have a cap on this. So yeah, there is a cap, and it will not use all, or it will not eat all your memory. So the third question, is there any limit on native memory usage? I believe it's the same as the second one, which I just answered. Okay, and the fourth question, during the demo, can you explain fully what the machine's layout was? How many Hazelcast members, how many clients? Is all traffic to across network? What kind of network? All right, so it was a fairly simple setup. So I had, I believe, 9 Hazelcast members. I was using the member-to-member topology. So there were no clients. So some people call it peer-to-peer. So it was really just Hazelcast members talking to each other, and not all the traffic was across the network. So I was using really random keys. It means that about 10% of my requests, they were local, and the rest was across the network. And I was using, I believe, 40 gigabits network. It was on our performance lab, and there are multiple networks, but I believe the test the demo was using the 40 gigabit network. So the next question, sorry, my audio was not too good. Did you say it is deterministic? If so, how I determine max port times for SLA? You will determine it quite easily, and that is by testing. So you will run a test, and the HD memory, unlike the regular garbage collector, is deterministic. So there won't be a sudden pause because of concurrent mode failure, as it is the case with CMS or G1. So if you run your tests, and you will see that the your worst time, the worst case latency is about 20 milliseconds, then you can be fairly confident that it will not suddenly be 10 times bigger, unless, of course, there is something funky going on in your hardware. With objects, okay. The other question is, with objects with different size, you are still exposed to fragmentation. Do you have something like mode failure? That is correct. We recommend to always have about 30% of a headroom. So if your expected memory usage or your expected live data set is 100 gigabytes, then your maximum native memory should not be less than, let's say, 100, 140 gigabytes, and then you should not really suffer from the fragmentation. So out of the next question is, out of 128 gigabytes RAM, how much percentage of memory can I use for native memory? That's a good question, and there is this most hated answer ever. It depends, and it depends on what else is running on your box. So is it just a single JVM, or are there other services collocated on that box? Let's assume that nothing else is really running on that box, so it's pretty much dedicated for your JVM, apart from some basic services from the operating system. Then let's assume that this is a dedicated JVM to act as a Hazelcast member. It means that there won't be your application running and using the memory. So it will be again pretty much dedicated to the Hazelcast. Then out of 28 gigabytes, so now I'm just my first estimate or first numbers I would start testing with would be, okay, you have 128, so keep 2-3 gigabytes for the operating system. Then maybe 1-2 gigabytes for the JVM heap. 1 gigabyte will be enough. Then maybe 1 gigabyte for the JVM internal native needs. Then maybe I would start with 120 gigabytes as a native memory, and yeah, I would use this as a early basis for testing. Yeah, so but things like this should always be tested. It's this 120 it would be a starting point for testing. But if you want to guarantee SLA, you always have to measure things. Yeah. So there are no more questions at this point. So if there is any other question, then please go ahead. There is. I can see now there is one more question. So what is the recommendation of how calculating the regular heap size and of-heap size? It's similar to the previous question. So assuming that there is no other application running in the JVM, then you will be fine with fairly low heap size. So I would start with 1 gigabyte again as a starting point for further testing. Okay, there are two more questions. So first, can we have overflow to disk if it goes beyond the limit specified? How does it behave when it reaches the NIO limit? It will fall back to heap. we do not have overflow to disk. What you can use is you can have a memory loader and memory maps. I'm sorry, not memory loader, map loader and map store. So you can configure an eviction policy, and you can say, okay, I want this map to take no more than 50 gigabytes of RAM. And if it goes beyond this limit, then I want some item, let's say least frequently item, to be evicted. And at this point, when there is some memory pressure and an item is being evicted, then we can call your map store implementation. That's something you will provide. You will write against our SPI, and then you can store it to some other system. Typically, it can be a database or whatever you fancy, really. Okay, there's one more question. Can we have overflow to disk if it goes beyond the limits? Okay, I just answered that. That was the second part. How it behave when it reach the new IO limit? Will it fall back to heap? It won't. You need to increase your NIO limit. No, sorry, no. The current implementation, it does use unsafe, so it will just bypass the NIO limit, I believe. But certainly there is no fallback to heap. But this is something fairly simple to configure because it's just one-off thing. Okay, how to make this? So next question is from Francis. How to make decision? How many nodes do I need for an application? Good question. So what I would do is first I would try to roughly calculate the estimate, estimate rather than calculate, to estimate my expected life data set. And once I have, once I know my data set, then again it depends on your use case. So if your use case is Hazelcast as a data grid or maybe a key value store, and you are not running any extensive calculations or computations, then you can maybe start with the HD memory. You can maybe start with just 2 nodes, so one for redundancy, and you can start your testing, and then we'll see what about the throughput. Is it okay? Is the hardware coping with this load? If yes, then great, you are done, and you have just 2 members. You have a redundancy. So if you lose one, you will still have the data. And if it's not enough, then or maybe you are not using Hazelcast as a key value store, but you are running some computations, then of course you need to scale out to multiple members. The next question from Francis: is On-Heap only beneficial for big objects? It is not. It is not, because it's beneficial every time when you have you really want to have some predictability, and maybe you have small objects, but you have plenty of them. Then the overall life data size, will not be small, and when it is not small, then eventually you will hit rather long garbage cloud. You may, that's the tricky bit. You may hit a long GC post. So no deterministic. It's not deterministic. The other question from Antonio. Is the enterprise version accessible from other languages? C#, MATLAB, R? It is. Actually, we have clients for multiple languages these days. So there's a client for Java that goes without saying. Then we have open source client for C++. We have clients for Python. and for Node.js, and I'm sure there are more being developed. Some are being developed by Hazelcast, and there are even some implementations being done by community. I know there is a guy who is working on a PHP client, and I know a guy is working on a Golang client. And yeah, the client protocol is agnostic to the underlying storage. So you can, of course, you can use the HDI or HD memory in general and access it from all clients, because this is completely transparent to the client protocol. And yeah, I forgot, we have C# client, yes, and it's also open source now, so you can call it from, you can use it from .NET. Okay, there is another question from Thomas. Considering the various garbage collection strategies and Java runtime environments, what strategy and runtime would you prefer to use for highly transactional multi-terabyte JCache HTTP session solution with over 200 gigabytes HD members? So assuming that you are really using the HD memory, then the actual garbage collection, garbage collector doesn't matter that much, because or even your Java runtime, because yeah, the data, they will be stored off heap, so they will not be visible for the JVM. So it really should not matter. When it comes to the actual runtime, Hazelcast, the recent version, or the all versions pretty much, since version 1, I believe, works on Java 6 and higher, so you can use it from Java 6, Java 7, Java 8. And we also have a continuous integration to make sure it will work from Java 9. And yeah, so it really doesn't matter when you are using HD. Okay, there is a question from Girish. Any serialization tips or optimization that would work best for new I/O you'd suggest? Yes. The tip number one, my tip number one or suggestion would be, do not rely on Java serialization, because Java serialization, the primary goal of the designers, the primary goal was not speed, and the primary goal was not space efficiency. So it's nice and convenient, you have your domain object and you just mark it as, implements Java I/O serializable, and you are done, and that's quick. But then it means it's not the best possible option. It will not be very fast, and it will also have quite some space overhead, because it will, the serialized version will contains all the fields and everything, and you don't need it. So the first really optimization is use something else. So what's the simplest what you can do is to implement interface, data serializable interface, which is Hazelcast specific, and that will make it's fairly easy. It has just 2 methods, read and write, and it will make serialization much faster and much more space efficient. And then, of course, you can plug in, for example, a Creo. That's fairly popular. There is no out-of-the-box integration with Creo, but it's fairly easy. Just a few classes of code. And I happened to have a community project which is not really associated with Hazelcast, or it's not Hazelcast official project. It's my spare time project called Sub-Zero, and it's intended to have no coding integration of Hazelcast and Creo. So if you want to use a Creo serialization, just Google Sub-Zero. Yes, I said it's not official Hazelcast project. It's not supported by Hazelcast, but it's the simplest way to integrate Hazelcast and Creo. The other question is from Girish. How does it work for in-memory equals object format? The simple answer, it does not. So it's mutually exclusive. So either you have the object format, it means that the Hazelcast will store your object deserialized in their object form, but you can't store, deserialized, object in off heap. So when you pick the native memory, the HD implementation, that it will always be stored in its serialized form. So it's mutually exclusive, and there is actually no way to configure object together with native. It's you need to pick one. Okay, the other question is, Hazelcast comes with default partition 273, I think it's 271. Can I use Hazelcast with the only one partition? For example, snapshot data not distributed. Yes, you can, and if you can use Hazelcast with a single partition only, but even when you are locally, so you have no data distribution at all, you have just a single JVM, you can still use it with default partition count. It's just all partitions will be owned by the single JVM, so it will still work. All partitions will be located inside a single JVM, and maybe eventually you will need more data to store more data, or you will need some data redundancy to have some backups. Then you can just start another JVM, and the partitions will be automatically distributed for you. So you will have some elasticity. And I have I always thought, okay, Hazelcast is great and everything, but maybe it's not the best fit for the local only use case. But I was recently told by my ex-colleague who doesn't work for Hazelcast that they actually use Hazelcast in the local only mode. And the reason is that they can specify own class loaders. So before they were using some other caching local only framework, but they had a problem with class loading because it was using the default class loader only. When it was deserializing objects, and it was causing some sort of issues for them. In Hazelcast, you can specify, if you want, you can specify your own class loader to use when, for example, deserializing data. So yeah, it's being used even for local, in local deployments. Question from Antonio: does IMAP support Java 8 features, streams, lambdas, etc.? Streams, it will work, but it will not be very efficient. But I believe it should work, but I wouldn't recommend it. We are working on the stream, on a proper distributed stream implementation as I am talking about this. When it comes to lambdas, it will work. It will work. You just need to make sure that your lambda is serializable. So in the Java 8, you can have an intersection of interfaces, and when you are defining your lambda, then you need to, for example, with the entry processors, then you need to make sure that the lambda is serializable. Otherwise, you will not be able, or Hazelcast will not be able to send it over the network. And there is a question from Yusuf. Still want more members for replication. Okay, so that's a continuation of the previous question. Okay. Oh, okay. So you want to have a single partition, but you want to have more members for some replication. This will not work. So a partition is owned by exactly one member, so you can't have a shared ownership of a partition. So if you have multiple members, then of course you need to you want to have more than a single partition. But honestly, I've never heard about anyone using just a single partition, so I don't understand the use case. There's a question from Thorsten. eviction policy can be based on LRU, or least frequently used. Yes, you can use both, and you can even, as of Hazelcast 3.7, you can also use your own or custom strategy. So you can basically, what you can do is to provide a comparator, the implementation of comparator, which will be used for the eviction. So if the built-in algorithms are not sufficient, then you can write your own, and maybe you can make a decision based on some business data. This is a new feature in Hazelcast 3.7. How are these timestamps calculated? Well, every time when you access an object, then the timestamp is updated, and we also maintain the hit count. So we have this statistics information, so you can use the one of the out-of-the-box policies, and it will just work. And as I said, if this is not access means get and put, or only put. To be honest, I don't know by heart, but just drop me an email at Jaromir, that's my name, Jaromir, at hazelcast.com, and I can answer it, or you can stop by at our Google Groups forum. So if you just Google Hazelcast user group, then you will find Google Groups mailing list, or we have a Gitter. So if you know Gitter, it's like Slack for the GitHub projects, and I tend to be there quite often and answer questions. So I can look this up for you and give you an answer. I don't know this by heart.
Great, and we are a little bit over time, but that's okay. But we're going to have to go ahead and wrap up with that. Okay, and thank you so much, Jeremy. That was a great presentation. Thank you, everybody, for your questions. We kept that going for a while, and that was excellent. And I hope everyone has a good day.
Yeah, thank you for your passion, for listening to me. And I like to say when I'm talking to people, happy Hazelcasting. And yeah, so yeah, have fun with Hazelcast, download the trial, and try HD. Yeah, bye-bye.